Welcome to Lecture 21A, entitled Definition of Circulation and Flux and Geometric Interpretation of the Divergence and Curl Operators. So this is basically now a teaching module which involves a couple of new concepts, and we'll be using these concepts throughout the remainder of the course. The material for this lecture comes from reading assignment 4, sections 1.8, 2.2, 2.3, and 2.4. The objectives are to understand the meaning of circulation and flux, and from this we're going to basically define what we call the divergence curl of a vector field. This was for 2D as well as for 3D. The concepts and visualization skills, first of all, are conventions, specifically conventions for tangent vectors and normal vectors. Then the concept of circulation and flux, and then the definition of divergence and how to compute the divergence of a vector field, and also finally the definition of a curl and how to compute the curl of a vector field. As usual, the second slide is just an outline of the slides to follow, so I leave it up to the reader just to go through each one of these particular items in turn, and we'll move on to the next slide. All right, so let's first start with a simple thought experiment. And we're going to stay with a two-dimensional representation of a field because it's somewhat easier to understand in terms of where we want to go using 2D fields because they're easier to graph. And so what I'm essentially stating is that if you take any vector field in 2D, then essentially we can break it up into two types of fields, which are essentially have completely different properties. One of these fields, which appears to be of a source type behavior, we'll talk about that later, and one which has a circulation type behavior. And we're going to start with a very simple field. Always start with linear fields because we can do lots of things with linear field in terms of developing intuition. And so what I'm essentially saying is that we have these two fields. This first field we'll call a flux field. And this is a radial field, xy. We discussed this earlier in one of the preceding lectures. And then we have another field which we're going to call a circulation field, which has this form. And this would mean that the field forms closed loops. And if we take the sum of these two, we're going to essentially say that this is the total field. So we're saying that the total field basically can be represented by the superposition of two fields with totally different properties. One of them which we associate with a source, and another one we associate with rotation. And so we've just added these together to produce this total field here. All right, so next thing we're going to do is we're going to find a contour, and we're just going to keep it simple, a circular contour of radius r. And you'll notice here, for instance, I have graphed the field, which is purely radial. This is F flux. Over here, circulation would be the black arrows that you should see here that form closed loops. And this one is just the sum of the two, which looks more or less like a spiral. Okay, that's the sum of these two fields produces a spiral. The contour is this one that you see in red. And we're going to be, by convention, we're going to be traversing this contour in a counterclockwise direction. And so the unit differential vector tangent to this contour is t bold ds for this, as well as for this. Also, by convention, if we're going around a contour in a counterclockwise direction, then the normal to this contour is to our right, which is what you see here as nsds. So this is basically the unit normal vector, the normal to the contour, this circular contour here. So the first thing we would do is parameterize this contour, and we're going to parameterize with an arbitrary radius r. And so this is the line that we see here, r being the radius, cos t sine t, and t ranges from 0 to 2 pi. So that would mean that this arrow basically makes one full circle as t goes from 0 to 2 pi. So TDS, we know how to do the calculation. This is basically unit tangent vector. You can just take the derivative with respect to t, dt, and this basically gives you TDS. Similarly, if you want the normal vector, which is going to be required, right? Then this is perpendicular to this, and we have shown before that this can be represented as r cos t sine t dt, and you can confirm that when you go around the contour in a counterclockwise direction, ns will be always pointing outwards in a radial direction. I mean, that's clear just by looking at this expression and this expression. They're essentially in the same direction, pointing outwards. Anyway, these are things to keep in mind. And so what we're going to do is now we're going to make use of the vector field and the different contours. This is a contour involving a tangent, and we're using the same contour. We're going to be making use of the normal vector component. All right, so we're going to compute the circulation and flux, and the circulation is defined as basically taking a closed contour integral of the dot product between the field, which is the circulation component, and the unit differential tangent vector, and integrating around the closed contour. Well, here is the vector f, again from the previous slide. Here's the vector TDS from the previous slide. We take their dot product and we integrate, and if you go through that process, you'll find you'll get an answer of 2 pi r squared. Now, we want to compute the flux, and the flux is associated with taking a dot product between a vector field and the normal to the contour, integrated around the closed contour. So in this case, f circle basically does not change, but now the second vector changes, and so you can see here, this is r cos t sine t dt. If you do this integration around the closed contour, you get a value of 0. If we now take the flux field, and basically perform the same integrations as we've done here, but in this case take a dot product with the differential tangent vector and integrate around the closed contour. F flux has this form, and the TDS basically would be this form here. This is now the tangent vector. Then we end up with a value of 0. On the other hand, if we do a calculation of the flux, right, using this vector field, this is a flux field form, integrating around, clearly this term here and this term are different, and if you integrate this you'll have 2 pi times r squared, r being the radius of the contour. Also, just to sort of be clear, what are the units? Well, since the units of this integral are we call circulation, and the units of ds are in terms of meters, that means that the units of f will be circulation divided by meters, and similarly circulation in the case of the field f, in the case that we're dealing with a flux integral, the units f would be flux over meter. So one observation we can make from looking at these results is that a field that only has a circulation component, right, which would be this field here, has no flux. So if you look at the flux calculation, we got 0. And a field that only has a flux component, so if we look here, has no circulation. So we end up with a 0 here. So it seems like essentially if we're able to break this up into two separate types of fields performing these two types of contour integrals, they act as a filter. They either tell you that the field is pure circulation or pure flux, or some combination of both, in which case both of these would give you terms. So the intuition tells us this might be very useful. All right. What about if we were now to pick a different location? So compute the circulation flux at an arbitrary position in the xy plane. So all I'm doing is I'm saying that create a little contour, but at some location x naught, y naught on the xy plane, and repeat the same procedure. All right, so TDS isn't going to change because once you take the derivative of this with respect to t, the x naught is 0, so we end up with the same value for TDS as well as NDS. And if we do this calculation now, given the fact that we're dealing now with a different circulation, and at this particular location, and do these calculations, we find that we end up still with the same value as before, 2 pi r squared. Similarly for flux, we still end up with 0. If we were to compute the circulation, assuming the field is pure flux form, then we end up with 0. And if we then calculate the flux, assuming the field is pure flux form, we end up with 2 pi r squared. So the general conclusion we can state based on our observations is that the circulation and flux for this particular example, not for all possible cases, these are basically linear fields we're dealing with, it seems like they're not impacted by the location at which a computation is performed. All right, so we look at those results and we say, well, maybe it might be useful to try and normalize these expressions for circulation and flux. And we noticed that basically on the right hand side there was a pi r squared showing up. So that pi r squared basically is nothing more than the area of the enclosed by the contour. So let's try to make the circulation flux integrals independent of the area. So what we're going to do is we're going to divide the circulation by the area. If we do that, we end up with a value of 2. So this suggests to us, by doing this sort of division, we end up with a number which does not depend on the nature of the contour. And that's helpful in terms of how we go about creating a definition. So similarly, if we take the flux and divide by an area, we end up with a value of 2. So the general conclusion that this form of normalization, which is dividing through by an enclosed area, allows us to make circulation flux independent of the contour chosen. And it's this procedure, basically, which will allow us to come up with these definitions, which we'll be showing shortly. All right, so this is just a sort of a simple example of what we've just discussed. This is an interactive simulation that you can click on, and you can see what happens here. You'll find that the variable slider t would be the movement of the observation point with respect to the origin. So this black dot can be positioned anywhere in the xy plane. The variable slider p is the rotation of position vector with respect to the point of observation. So that's little black arrow here. It's basically just moving around, and the shaded circle area, which is shown in pink, the brightness of color represents the strength of the source basically being, in this case, flux, which is obtained by computing the integral. So if that value becomes larger and larger, then this color will change. If it gets smaller, it will be changing a different way. But in this case, we said that the flux was independent. The flux divided by area, or flux for that matter, were independent of position, where we placed this dot on the xy plane. And therefore, if you move this around, you'll see that this color never changes. And so that's something sort of to tell you that at this location, there appears to be a source, and that source basically is independent, the magnitude of that source is independent of where you position that little circle on the xy plane. All right, we can also do it for the circulation divided by area. In this case, here's the field, the circulation field. And if we were to do the computation of the circulation divided by area, again, idea be here that the variable slider t is the movement of the observation point with respect to the origin, which is this black dot that you see here. The variable slider p is rotation of position vector with respect to the point of observation. So the little black arrow here, which basically sweeps around, makes a full circle. And the red vectors, which are pointing upwards here, represent the strength of the circulation, which is the magnitude or the length of these red vectors that you see here, and the axis of rotation, which is the direction of the vectors. In this problem, the strength is a constant, which means the magnitude of these vectors are independent of where you may position this little circle on the xy plane. So this is again peculiar to the fact that it's a linear field. Now clearly here, as and perform, what you'd like to do is to make the circle smaller and smaller, so that you focus only on the point of interest, which is the observation point. So we were trying to figure out what is the circulation-like behavior right at this point, which means a limiting process would make this circle smaller and smaller. And that's basically how we formalize the definitions for what we'll call the divergence of a vector field and the curl of a vector field, which is basically the subject of the material that's coming up. All right, so we're now at a stage where we can basically come up with a formal definition for the divergence of a vector field in 2D or 3D, representing the source type behavior of a vector field, and then looking at the rotational type behavior, which we'll call the curl of a vector field in 2D as well as 3D. So we'll begin with the 2D formulation of the divergence theorem, and it's basically stated here in a differential form. That is, we're going to compute the flux around a closed contour, and then we're going to divide by the area, which is basically enclosed by the contour, and we're going to let the area go to 0. So we're basically focusing on a single point, and we're basically interested in the divergence of the vector field at that given point. The units of f for the flux integral are flux per meter, and this can be seen clearly by the fact that if the integral is flux and ds has units of meters, then f has to have units of flux per meter. Now the choice of the contour here
is basically immaterial, so we've chosen the simplest type, which is more or less a rectangular or square type structure. And so we would be typically traversing the contour in a counterclockwise direction, in which case the normal to the contour would be pointing to your right. So along this segment, the normal points here, the normal points here for this segment, the normal points in this direction for this segment, and the normal points downwards for the last segment. So a closed contour integral in this case would basically be represented by 4 individual discrete integrals, each basically being a flux, but when summed together would be the flux enclosed. The field values that we're looking at, the ones we care about, are only the ones where the field is parallel to the unit normal vector to the contour. And so you'll notice here that in this location, the normal points outwards, which means we only care about the y component of the field. It's the only one that makes a contribution to the integral. On this side, it's the x that makes a contribution. Here are the y, and also here the x. Notice that we keep the direction of fx on this side and this to be in the same direction, aligned with the coordinate axis. Similarly, y is aligned with the y coordinate axis. And A is the area enclosed by the contour that's seen here. All right, so what we need to do is to compute the contour integral, closed contour. And here I've just shown it as 4 individual segments. And the subscripts y, x basically indicate which component of the field basically makes a contribution to an individual flux component. And so this is basically the 4 integrals that we need to compute, given this picture shown here. Now, we shown earlier that this particular dot product integral can be replaced by fx dy minus fy dx. And you recall that when we dealt with contour integrals, that we could express the unit normal vector ds as y dot x dot dt, or this can also be expanded out in the form of explicit form as dy minus dx. So this would be the parameterized form, this would be the explicit form. We're going to leave it in explicit form, so it'll be in this form. And so if we basically apply this definition for NSDS, right, and then this is basically the f dot NSDS, and we do that then for each one of these 4, then you can essentially see we have 4 contributions. There's one here, there's one here, one here, and one here, and the area is dx dy. That's basically this differential area element. Now you'll notice here that dy is common to the denominator and numerator, and so they cancel. And here, dx is common to numerator and denominator, so they cancel. And so what we're left with here is fx valued at x plus dx minus f of x valued at x divided by dx, but that is nothing more than the definition of a partial derivative of f of x with respect to x, which is the first term that you see here. The second term that you see here basically is replaced by df partial y dy. And then what we do is we apply a little trick. We essentially realize that this could also be written as in the form of a dot product between 2 different vectors, but the vectors have different meaning. So for instance, we could create a vector which involves the partial of x and partial of y. We call this the gradient operator. This is something we saw earlier in the course when we dealt with the gradient. And this is dot product with the actual field vector itself, the x component, y component. So if you apply the dot product formula, then this partial x operates on fx, this partial y operates on fy. But if you take this as a whole, this can be replaced by this del operator, and fxy is just by definition is the field vector. So this symbol, we call the divergence of the vector field f, is equivalent to performing this calculation in the limit that you see up here. So effectively, we've shown now how we get to this symbolic form of the divergence of a vector field in 2D. And the units of the divergence of f would be basically just the flux divided by meter squared. You can see this directly from here. If this is flux by definition and this area is meter squared, then divergence of f would be flux per meter squared. All right, now let's look at the formulation of the divergence theorem in 3D. Now in 3D, basically, we have to create a volume, and the volume basically is enclosed by 6 individual discrete surfaces. Again, the nature of the volume is not important. We want to make the calculation simple, so a simple cube basically will suffice. So you'll notice here, in this case, the outward normal vector is always pointing outward from the surface. This again by convention. And you'll see, for instance, here, this is basically a normal pointing in the y direction. This is a normal pointing in the x direction and a normal pointing in the z. There's the left face and the right face, and front and back, top and bottom. Since we're going to be taking a dot product to compute the total flux emanating from this closed surface, then the only contribution of the field for this particular surface is that component which is in the same direction as the normal to that surface. So for this particular differential surface area element, which is in the direction of z, only the fz component makes a contribution. And since there are 6 individual surfaces, you can see there are 3 individual open surface integrals. We can basically define each one of these differential surface area elements for each one of these 6, and these are basically just indicated here. Again, always pointing outwards from that particular surface. Here's the actual definition in the limit. We're basically taking the total flux and dividing by volume and letting the volume go to 0. And the units of this flux are nothing more than the units for F, for the field F, are flux per meter squared. All right, so next step is to take essentially all the information provided. We know what these field components are, and making use of this diagram, we essentially have created 6 contributions to the flux integral, closed flux integral. That's these 6, and these are the ones that you see shown here. I've grouped them, in such a way that all the x's are together, all the fy's are together, and fz's together. Now notice in this first term here that dyz is common to the numerator and denominator, and so they can be basically cancelled out, and we're only left here with dx. So here we have an f of x and f of x, but by definition, this is the partial of f subscript x with respect to x. Similarly here, we get cancellation of dx dz, and we're just left with dy. Well, this is partial f per partial y, which is this term that you see here. And the last one, basically going through similar arguments, is just dfz dz. Now, again, using a trick that we adopted in the previous slide, in this case, we can describe this basically as a gradient operator, but in 3 dimensions, 3D, right? Partial x, partial y, partial z, and the vector field f, which has an x, y, and z component. But this can be written out as del. This is in shortened form, and this is just the vector field f. So this is basically the final result we get. This is the divergence of vector field f in 3D, where this del is now interpreted as being basically a vector with 3 components, and f also having 3 components. And so this is another way of basically saying we're doing this calculation shown here at the top. All right, now that we have taken a look at the divergence, now next is to look at curl, in other words, the rotational component, and look at the definitions when we make everything infinitesimal. We'll start basically with 2D, and so the simplest thing to do is to essentially pick y-axis, and what we've shown here is again a contour traversal, but in this case we're dealing with the tangent to the contour, whereas with the divergence it was normal to the contour. So this is basically the tangent to contour. The area, of course, enclosed is this one, but according to the right-hand rule, the direction of the axis of rotation is pointing in the direction of the thumb. So if you curl your right fingers in the direction of the contour traversal, that means you're pointing outwards, hence the z hat, showing the direction of the axis of rotation. All right, so these are the conventions that always need to be kept in mind when we're dealing with the curl operation. And so what we're going to do is just let this area go to 0. In this case, the units are different. So anytime we see something in this form, we say that this closed contour integral is basically its circulation. But ds base has units of meters, and therefore f in this case would have units of circulation per meter. All right, so because these are discrete line elements and not a continuous contour, it means that this closed contour has to be broken up into 4 individual segments. And again, we know from previous results that if we take the dot product between the field and and the differential tangent vector. This is equivalent of fx dx plus fy dy. And recall that t ds, t being the unit tangent vector, x dot y dot dt is equal to dx dy. In one case, we're dealing with an implicit, a parametrized representation, but we're going to be using the explicit representation is the one shown here as dx dy. All right, so all we need to do now basically is to do each one of these four integrals. And so this picture and these expressions that you see here basically, this expression is taken from this picture. Notice a of z basically is just the area of this this area here, which is enclosed by the contour, which is just dx dy. And again, you'll notice here, for instance, dy is common between numerator and denominator, so you get cancellation. So now we have f of y dx in this case. In this case, we have dx is common, numerator, denominator. So this is fx dy, but there's a minus sign. So in this case, we end up with this simplifying down to dfy dx minus dfx dy. And so what we're going to do is we're going to give this a special symbol. We're just going to say that this is equivalent to the curl of the vector field f, and this is the z component. Z meaning that the axis of rotation is pointing in the z direction. So this is just a short form for this expression that you see here. Now, what are the units going to be? Well, the units are going to be circulation divided by meters squared, and you can show that fairly simply just by looking at this expression here, which is the same thing. This is circulation area as meters squared. All right, so how do we go from this notion of, curl in 2D to curl in 3D? There's only one thing to consider, and that is in 3D, we're no longer talking about a single plane, but we're talking about three principal planes. And so we have basically one plane, right, which is in the zy plane. We have one plane which is the zx plane and one plane which is the yx plane. This is the one we've just considered when we were dealing with a pure 2D problem. And of course, we mentioned back then that the axis of rotation was in the z direction, but strictly speaking in 2D, there is no z direction. So we basically treat it as an imaginary axis. But in 3D, the z-axis does actually exist, and so we can actually say that this is a z hat. All right, only thing to recognize here is that in all of these cases, we have to make use of contour traversals, which are counterclockwise, and we also have to make sure that we abide by the right-hand rule and right-handed coordinate systems. So y is pointing in this direction, z in this direction, so by definition, x will be pointing out of the page. In this case, we have z pointing in this direction and x is pointing in this direction. And so by definition, according to the right-hand rule, if it's a right-hand coordinate system, the y-axis is pointing out of the page. And then this is basically, if this is the y-axis and the x-axis, then according to the right-hand rule, a z-axis is pointing out of the page. So these are conventions we have to make absolutely certainly that we abide by, otherwise none of these expressions have any meaning. All right, so when we're dealing with rotation or circulation, curl in the ZY plane, then this is basically the definition that we're dealing with, and we're going to let the area go to 0. Similarly, if we're dealing with a rotation in the ZX plane, then basically we're dealing with this formulation here. In this case, the area is AY, and we let AY hat go to 0. And lastly, if we're dealing with rotation in the YX plane, then basically we're letting the area Z go to 0. So that's this formulation here. So we've done this calculation for the 2D case. So we just can basically redo this type of calculation for these three individual cases that we're looking at here. And what you'll notice in this case, you've got fz partial y minus fy partial z. The form of this and the form of this and form of this look the same. The only difference is you're exchanging x's, y's, and z's. And so there are differences here. And so what I've done is written this all out now. You can essentially see that when you do the actual calculation, for example, for this particular case, the AX hat case, right, then this just becomes the expression we've seen here. Right? And so, again, the key point here to remember is that when we're dealing with 3D, In 3D, basically, rotation is defined on a primitive plane, which is by definition two-dimensional. But in 3D, we basically know that there are three principal planes that define a 3D system. And so we need to determine the rotation with respect to each one of these principal planes. And so these are the expressions that you obtain.
All right, so here was the x contribution that was pointing in the x-hat direction. This is for the yz plane, this was for the xz plane, and this is for the xy plane. So what we can do is we can write this in determinant form in this form. So we could say that the x-hat component could be written in this form, y-hat component can be written in this form, and z-hat in this form. And so I'm going to call this the x-hat component of the curl of a vector field. Why the cross product? Because this is typically how we express things in cross product form. So this would be the x component of the curl, this is the y component of the curl, and z component of the curl. But I can add these all together, right? And it's just basically add them all together, and I end up with this final form, which is by definition going to be the curl of the vector field f. So first row being the unit vectors in Cartesian coordinates. Second row would be the first vector, which was just the gradient vector. And the third row would be the field vector, the x, y, and z component. And if you want to show this in diagrammatic form, just look on the right-hand side. Here are your three principal planes. Here basically it shows the contour traversals for the individual planes. Each one of them makes a contribution, and the total value, which is the sum of all three, is this vector that you see here. So that represents what appears to be the apparent rotation of the field at that location, taking account the x, y, and z component. And so that's the curl of f. All right, so just a brief summary of some of the things we alluded to earlier regarding in 2D, that the axis orientation, axis rotation was out of the page. Of course, in 2D, the z-axis does not exist, and so we have to define it as an imaginary axis, and so we use that, define that as a pseudo-vector j. Similarly, for the situation when we're dealing with real numbers, where we could not basically define what was meant by the square root of -1, so we just gave it a label and called it j and called it an imaginary number. Now, we basically know that the imaginary number is a scalar, and we know the real number is a scalar, but if we want to basically depict both of them, then effectively in 1D, which would be a real number, would be along the x-axis, we can essentially use the y-axis to describe the imaginary component when we're trying to basically plot values for in the complex plane. And so effectively we can then recycle the notion of a vector, and so we talk about a complex vector rather than a real vector. So these examples here just show you different ways and things that can be written. For instance, a pseudo-vector could be written as a scalar multiple times j, this being a pseudo-vector. Or you could essentially say a is a real vector and multiply by j, with j being basically an imaginary number. This also can be considered as a pseudo-vector. And this is just some geometric properties. What exists? Points exist in 1D, 2D, and 3D. Lines exist in 2D and 3D. And oriented planes exist in 3D space. And to summarize, I've just put the properties of the pseudoscalars in one column, and the properties of pseudovectors on the other column. And in fact, the reason I've put this here is because if you look from a historical point of view, how did vector calculus start? It dates back to the late 1800s, and there were two competing approaches. One which was based on the Gibbs formulation, which was intuitively simple to understand. And then there was another one which was based on concepts of algebra and geometry and putting them together. It was at that time too complicated for many people to understand. And yet, in hindsight, it's much easier from an intuitive perspective to understand vector calculus in more than 3 dimensions if one goes the route of geometric algebra. Whereas it becomes much more difficult to take the Gibbs formulation and extend it to higher dimensions. So today in computer science, when we're dealing graphics, geometric algebra is the approach that most people are taking. All right, so that concludes Lecture 21A. Thank you for listening.